Okay. Okay, welcome everyone. Welcome to IISE Transaction webinar series. My name is Yu Ding. I'm editor-in-chief of IISE Transaction and I'm faculty of Texas A&M University. IISE Transaction webinars featured a series of talks based on the article in a special issue to be published in the January issue of 2023. And today is our last webinar in fall 2022. We are very delighted to have Dr. Elise Miller-Hooks with us today. And she holds the Bill Eleanor Hazel Endowed Chair in Infrastructure Engineering at George Mason University. She is on faculty of civil engineering, but also very, very active in Informs. And she's serving as associate editor for Operations Research, the flagship journal of Informs, and served as the past president of Informs Transportation Science and Logistics Society and the Women in ORMS Forum. Dr. Miller-Hooks is the founding editor-in-chief of Elsevier's Sustainability Analytics and Modeling Journal, and also advisor to a World Bank Group. Dr. Miller-Hooks was inducted into the University of Texas Civil Architectural and Environmental Engineering Academy of Distinguished Alumni in 2021. So today she is going to share with us her thoughts on constructs in infrastructure resilience framing. And Alice, we are so delighted to have you here today, and the platform is yours whenever you are ready.
Thank you so much. I'm really glad to be here today to share my thoughts on the role of framing and perspectives in resilience computation. Here, I'm going to share with you here our list of webinars given in association with the special issue of IISE Transactions. You see the QR code in that top is for the paper in case you want to grab the paper on the side while we're going through this. And that's for the perspective paper. As a last speaker for this webinar series, I have the opportunity to thank you on behalf of all the authors of the articles in this special issue of IISE Transactions. Your vision pushed us to write these articles and pull our thoughts together on several very important, timely, and often difficult topics. Thank you for all your hard work to make this happen. When you first came to me about writing this article, you probably remember that I said, oh my gosh, I don't want to write a literature review of resilience because this area has exploded since I first started working in it. And when we started working in it, there wasn't even a word that we knew for sure to use. But then there are now many review papers since that time, and the word resilience has become ubiquitous and is used in a myriad of ways, and it's almost too broad to bound at this point. So today, and in my article, I do not attempt a review of the works in this area. Instead, I'm using a focus on the built environment, and I share my thoughts on how framing affects resilience computation and our understanding of whether the component or system we are concerned with is resilient. So buildings provide shelter needed to sustain life and support community services, such as business, manufacturing, health, religion. And the ability to support these functions depends too on access to functioning power and water supply and transportation, communications, and so on. And in the US and in many other locations, these systems are aging, they're operating at capacity limits in vulnerable, they're located in vulnerable locations because we love to live in vulnerable locations like the shores. And as a result of increasing dependence on cyber technology, they're more vulnerable to intrusion and they're connected with each other. So buildings and their supporting lifelines are subject to disruption events that induce damage. Such events might be caused by natural occurrences or accidents or engineering and technological failures, human-induced events of malicious cause, and yet the built environment is crucial for societal function. Therefore, it is important that our built environment and supporting infrastructure systems be resilient. There are a variety of definitions of resilience for this context. I give a few here on this slide. Generally, the resilience of a system can be described in terms of its inherent coping capacity and its adaptability. And resilience can also be thought of in terms of an action framework that I showed here. These actions can be taken to improve resilience, and they can be pre or post-event. So pre-event actions would be mitigative. They might be preparatory in nature, so they have no value unless the event occurs. And generally, they're looking to ensure continuance. Post or peri-event actions are aimed at impacting rapidity, and that's the speed at which the system returns to its ordinary or some target level functionality. Or it might, these actions could be related to response. And so you see the types of actions that can be taken and which actions determine whether they're pre or post event, and which determines whether or not you're talking about resilience or robustness or some other factors. There have been many different approaches to modeling resilience that go back at least until the 1990s, when Hames and others worked on and focused on security, redundancy, robustness, and resilience. Very popular paper that many have built on is by Bruneau and others, where they look at the 4 R's of robustness, redundancy, resourcefulness, and rapidity. And you can see these combinations can come from this action framework. And there's also the role of human action, which may be planned or it might be through innovation. So resilience can be measured as a function of performance achieved by a certain period. So that would be what we call point resilience, or it could be a total level of recovery achievement over a time period, and we would call that period resilience. And a metric like full or target level recovery could fall under a period resilience, or time until that occurs. And the actions contribute to both point and period metrics. So generally, resilience can be quantified through agnostic metrics, like I was mentioning earlier, that aim to provide consistency, generalizability, and broad applicability. So we really like these kinds of agnostic metrics. So it might be given as a number like a 0.5 out of 1. And consistent with prior definition, the idea that a system is resilient if it can maintain or reattain an acceptable level of functionality, considering the hazard event scale and type of event at a reasonable cost and level of effort in an acceptable amount of time, underlies this presentation and also the paper. And as is important, as important as it is, here I do not consider long-term recovery, such as population migration or land use changes, despite that these are really important things to consider. There have been hundreds, maybe even thousands of works in recent, maybe even the last decade or 15 years related to resilience that you'll find in the literature today. And they, many look at infrastructure resilience in one form or another, and they tackle many different problems of the built environment. And these are some examples where we'll find many publications. Inherent to most studies, like those I just mentioned, including my own works, across applications is an implicit construct for framing resilience. And this paper is about the role of framing in resilience evaluation and how framing and perspective affect models and solution methods needed and our resilience understanding. So I'll preface this by saying that I also did not realize that we were taking a perspective or thinking of a way of constructing the way we look at the problem and how it affects the outcomes very much until pretty far into our work and many, many different applications. And I'm going to share some of that today. So underlying, there is this underlying assumption of most resilience works that provides services, that the provided services will be more resilient if the physical buildings and lifelines that support them are themselves resilient. And I offer 5 key resilience framing constructs that somewhat build on that, but then try to take it a little further than that. This is only part of the story, however. The remainder of my talk will describe these constructs and the pieces that are also missing. So here's the first idea. It's the first construct, and it's one of a single structure or a single component, such as a building, or I show a picture of a bridge here. It could be a substation and a power network. It could be a pump and a water supply network. And a majority of structural engineering works in resilience take this type of perspective. So you'll see a lot on bridges. Broadening, though, from the single component perspective is a single system perspective. So we consider an individual lifeline, such as a roadway network is illustrated in this picture. And each lifeline network consists of multiple types of components, like here, the bridges and pavements, but they serve a single purpose. The system is considered from a technical or engineering perspective. And in the following 3 slides, I provide examples from my team's work related to ports, airports, and roadways of the use of this construct. The purpose of these 3 examples that I'll show you in a moment is to show that despite their different purposes and very different mathematical modeling approaches used in the resilience quantification, they all fall under just this second construct. And when developing these works and works on many other applications in mode, we did not consider any notion of framing when we were looking at these things, as I mentioned earlier. So here, in our very earliest work, we had applied our concept to consider the resilience. At the time, we didn't know what to call it, though. We were calling it flexibility at the beginning, and then started thinking it was resilience from the some of the nature-related works we had seen out there. And we were looking at a railroad system, national system. And it was for cargo transport, and it involved ports and terminals. And then later we looked at specific terminals, and this is a slide that talks about that work related to a specific port. So we applied this concept that I'm showing you here for port resilience. We devised a mathematical model that accounted for coping capacity and adaptive actions using a stochastic integer programming formulation. And we estimated resilience from a performance metric related to expected throughput over 10,000 scenarios of event impacts that might arise from 5 different disruption classes. You see here a concept also called point resilience. It's a little bit different from the one I mentioned earlier. So we have this mathematical model, and we have our outcomes from looking at the port. Later, we incorporated pre-event investments to create a 2-stage integer stochastic programming formulation for resilience computation in general. And then here we showed how to apply this concept to the resilience of an airport, in particular its runways and taxiways. And we considered the model as part of a decision support tool or decision support system with an optimization core that you see at the center here. And here resilience is taken as a function of the number of takeoffs and landings of small and large aircraft. And it's given combinations of effort levels and time for taking adaptive actions, creating what we called resilience indifference curves that are shown here. The general mathematical model for this resilience computation with pre and post-event resilience enhancement actions or adaptations, along with added constraints. If I go back a moment, you'll see a lot of added constraints for the specific airport application, is more complex and more difficult to solve than was our first port-related application, because we then introduced these first-stage decisions that come pre-event, which then makes the problem more complicated to solve. In the third application, we looked at roadway users and roadway resilience. And we developed a mathematical conceptualization here where we're looking at, instead of the flow of cargo and aircraft, we're looking at the flow of people. And people are cognizant. They can make their own decisions that serve their own best interests. We therefore used a bi-level mathematical conceptualization of the problem with a 3-stage stochastic program at the upper level that aligned with the disaster cycle and response of the users to what is offered to them is given in the lower level. So it sort of feeds back to the system. And resilience is measured then as a function of travel time delays. So in these examples, we consider only one system at a time. We take an engineering approach, and we might be looking at different users that have very different models, but they all fall under that second construct of an engineered single system. In this next construct, we'll look at systems of systems, which is also well studied and well thought about. We have a lot of interdependence work in the resilience field for lifelines in particular. And so we can consider multiple interacting infrastructure lifelines as depicted here. I added the the electrical power with the substations, feeders, to this picture to show that there's interactions. The interactions here arise because they're in a disaster event. You'll need the roadways to access the power system to be able to repair it. So one of the big areas that you'll see in infrastructure systems interdependence modeling is what we call WET, the water energy transportation nexus. It comes up very, very often. So in systems of systems, there are direct and indirect dependencies and interdependencies that arise in physical, functional, informational, spatial, logical, and economic causes. They can cross any subset of infrastructure lifelines, of which many are listed here in this slide. Here is an example that involves resilience of a traffic network given its dependence on power, in particular the power distribution network, where interdependencies arise, as I mentioned before, due to the crews using the roadways to fix the power systems. So here you see the road network, and then we have the power system network. So we have substations and feeders, and we can have other components, and these networks become connected, and we model the problem of assessing the resilience of the transportation system as a bi-level program where we have response of the users of the system who are working through their way through a traffic network with traffic signals that are powered by the power network. And so we have kind of a similar formulation, as I mentioned earlier, because we have that response of users who can make their own decisions. This problem was the first time that I'd worked on something where we started asking the question, who's resilient? So on the one hand, we can think about the transportation system, which was my initial goal, but then what about unmet power demand? And so there's actually an interplay between these systems, and we need to think about the different perspectives. Again, though, this is an engineered systems perspective. In the fourth construct, I now want to focus on taking the problem and flipping it and thinking about it from the user perspective. So in all the other applications I described, we were looking at the systems perspective, and thinking of it as an engineered system. But here, if we take a service-based approach, we can consider, rather than the technical component or the system functionality, the user's experience with the system. So this viewpoint induces a change in perspective with rippling impacts. It affects the choice of metrics for measuring resilience, the adaptation strategies to include in the assessment, the baselines for comparison, and elements and systems of the built environment to incorporate in the evaluation. It necessitates consideration of a socio-technical system and brings hidden issues of inequity to the foreground, which I'll talk a little bit more of at the end of this talk. So many of these aspects may be omitted from consideration in a purely engineered system or in a technical system viewpoints. And so taking a user perspective in investigating the resilience of a single technical system, as in this fourth construct, also induces interdependencies with other systems that may not be recognized unless we take that new perspective. So here is an example from transit, where we looked at the resilience of the transit system, and instead of looking at the engineered system, as we did in the other examples I gave, we took the perspective of the transit users. And we considered the level of service as the key performance metric, and diverse populations with different coping and adaptation capabilities use the system. So users, depending on the population from which they come, will experience the system differently and will have different levels of service, even for the same engineered system functionality. It is actually this kind of socio-technical system. So additionally, the user adaptation strategies will likely include the use of internet and communications, and that induces a coupling of technical systems that we wouldn't have recognized if we looked at it at the transit system from a technological perspective. So you think about users who are savvy and call for a ride hailing, or they go in to look at what's going on and they go on the web to see if the transit system is giving them information that can can aid them in their adaptation to whatever failure or disruption that is occurring. Moreover, the baseline performance of the various populations will differ. So you can imagine that if you rely on elevators and escalators to be able to access the transit system, and one of those systems is down, it could have a great impact on you, where others it might not matter. So this, it complicates the way we look at this, and we cannot take just one population's perspective. That is, if we try to look at the system from one population's perspective, we won't account for that the different populations share capacity, and there might not be enough capacity for everyone in certain circumstances. So we have to look at them simultaneously. It makes this very complicated. So a resilient system here can be defined by probability thresholds being met for certain performance levels. So you can imagine that one population may ordinarily not get as good service as another population that has certain advantages, and their baselines may differ in ordinary circumstances. So when we use an agnostic metric that uses any kind of baseline, which most do, you're going to get different values, and you'll have to think about, well, do I use the perfect baseline? Which population's baseline do we use? Do we use population-specific baselines, and so on? And there are trade-offs. One population may fare better when one population does worse. And how do we decide if a system is resilient? And if we think about the different populations, by reframing the resilience assessment of the transit system from the user's perspective, rather than taking the engineering systems perspective, as we did in the first three constructs, this creates very different outcomes in our resilience analysis. In our fifth construct, the last main construct, I introduced this concept we call CIBS, or critical infrastructure-based societal systems. And here we have a network of buildings with similar function, supported by interdependent lifelines that together enable the provision of a service that comes from those buildings. And so we can look at healthcare delivery or governance, education, religion, and so on. And by looking at this construct, we focus on the resilience of the service that the built environment is seeking to provide, given that that service is coming from buildings and that those buildings are relying on the functionality of lifelines that themselves are interdependent. So here is an example from our earlier work where we had healthcare or hospitals, like a hospital network at the top, and that the buildings are reliant on that WET trilogy that I mentioned earlier, the water, energy, and transportation infrastructures. So the buildings in which the hospitals are providing their services are dependent on those lifelines, and that has to be accounted for in the mathematical model. The approach we used here is a simulation optimization approach where we incorporated within a multi-stage stochastic program a meta model of the waiting times that patients incur from a simulation model of that with a lot of detail for individual hospitals. And so that's embedded within the simulation. We do not ask about the resilience of the underlying lifelines. Instead, we focus on the resilience of the community function itself, though the performance of the underlying lifelines directly impacts the assessment. In writing this paper, I had some feedback from a reviewer who said, well, we don't do anything in buildings anymore. Maybe you want to rethink this. And so it challenged me and made me rethink the CIBS concept a little bit. And I think we can think about this today as we sit together in this Zoom room, that here we are spatially, geographically disaggregated, or I don't know what the word is, far apart from each other. So in this age of digital-based services, the CIBS-based construct could frame resilience of virtual gatherings and workspaces in terms of the geographically dispersed buildings that house individual participants like ourselves with services that rely on lifelines, especially power and communications. But in this case, the supporting lifelines may not be interdependent as typically regarded, as they may exist across a wide area of, across the globe even. So my reliance here in my home, from which I'm giving this talk, on power from my locale, will not interrelate with any of you who are joining us today and the power system that is powering your computers that you're using to view this. So this actually makes us sort of rethink this virtual world, but noting that even in the virtual world where we sort of don't need to be together in space, we still are reliant on the structures that we house ourselves in and the interdependent lifelines that support our structures and the ability for us to perform any kind of function from the structure in which we're housed. Okay. Sorry, I should have had that piece up. All right, so here we have looked at 5 different constructs just to remind ourselves of what we said, what we were looking at. We start from a component, we look at a single system, a system of systems. We flip the question and now look at it, the systems from a service perspective or a user perspective. And then we move to that SIBS construct, or SIBS plus the digital age. Let's revisit the underlying assumption again, that services will be more resilient if physical buildings and supporting lifelines are resilient. So what is missing from this? And in our hospital work, we focus on staff, stuff, and space. So far, we've really only been talking about space, right? The physical infrastructure. But we really need to be thinking about, well, how do we provide services? We don't just need space, but we also need personnel resources or the staff. We need the equipment and consumable supplies, the things that help us supply our services from within these structures. So even if the buildings and supporting lifelines function perfectly, service capacity may be poor, as this capacity depends on more than just the functioning space. And so we revisit our hospital example and think about what are those personnel resources? Well, we're talking about doctors, nurses, technicians, and the like. And we're talking about in blood and oxygen and clean linens in terms of consumable supplies, and in terms of equipment, we might need MRI machines or other types of equipment. So buildings and supporting lifelines may function, but service capacity depends on more than that functioning space. It depends also on the things that we need to provide that service. So now expanding on the service-based thinking, we have talked about the role of humans in resiliency, and many works have recognized this. And we discuss this in terms of the need for trained personnel, delegation of authority for decision-making during disruptions. In my work in urban search and rescue, I've learned a lot about emergent behaviors. So if somebody's in the vicinity of the event and where there's been some collapse of buildings, some of the people who are there who have saved themselves are then most likely to be the ones who save others. So that's considered emergent behavior. But the ability to provide services, including services of supporting lifelines, requires these resources, the human capital that I just mentioned. And I want to expand on that concept from the SIBS to introduce this idea of soft infrastructure. So here I think of all these pieces in terms of gears that come together to create like a machinery that pumps something out. So here we conceptualize the buildings as gears, and we have in the buildings the human capital, permanent equipment, and so on. As I mentioned, the space, and those things turn together to make the larger building gear turn. And the buildings themselves can come together to provide functions like education and so on. And they rely, though, on working supply chains that provide raw materials and that provide the materials they need that are dependent on themselves on raw materials and middle products and transportation to the end users. So the supply chain gear is purposefully sort of connected to the different buildings and help make the buildings function. And then the buildings and supply chains themselves are supported by the infrastructure lifelines. And those themselves are interdependent, so I put them into one gear. And then we can turn this whole thing into this sort of machinery where the buildings, based on their connection to supplies of the materials that they need and also the personnel, can turn together. I plug them into the critical lifelines, which then sort of powers them. And as they turn to create the functions of the community. So here are just some ideas of what those functions are. This approach provides a general framework for building a mathematical model for computing and optimizing resilience of a particular SIBS that is expanded here to incorporate the space, the staff, and the stuff, as I've mentioned here. The model that I'm showing you here is bi-level, involving investments in the infrastructure and resources that support services from the SIBS. The staffs and stuff are embedded within the model through the mathematical equations that map personnel, equipment, and consumable resources to the service capacities. And you'll see here I have a lower level. I'm not sure if you can see my pointer, but at the lower level, I get feedback for assessing the service experience of the users of the SIBS who are gaining access to the services that are provided by the SIBS. And probable hazard impact scenarios are the effect of these probable hazard impact scenarios are felt in the upper level. And these kinds of things can lead to physical damage, but also absenteeism, supply chain disruptions, and so on, which can also be embedded here. So the scenarios are fully realized in the last stage of the multi-stage stochastic program at the top level. And the multiple stages can capture investment decisions and adaptations taken over the different phases of the disaster management life cycle, like I mentioned earlier in our earlier works. And there are various stages of the recovery process that can also be modeled with that multi-stage approach, which we did with our SIBS approach originally with the healthcare system that I mentioned earlier. So if I take that construct 5, and now I pull all these pieces in to put this drawing together, I put in the pipelines, I put in the communications, which I'm not sure I had before. There's the supply chains that I'm showing through the trucks that are coming through on the roadways that they're relying on, and so on. You see that they're connected to a port at the bottom. And I also have then my goal of, I put the hospitals as the main goal at the top. So you see the last thing I added here is the location of the personnel who live in these high rises that I'm depicting of, sort of living space. And they too must be supported to be able to support the hospitals. So the personnel living in these locations have to have transportation, and there's the little buses showing that they maybe use transit to get to the hospitals or use their own cars. But they need to be able to access the roadways and access the hospital facilities. And they need to be functioning themselves. They need a livable space where they can go to sleep at night and care for their children to be able to function in their jobs. So all of those things need to be accounted for here. So here I have the hospitals at the top. I add the human infrastructure and supply chains. The hospitals need access to power and water. You need to be able to access the hospitals. We need equipment and beds, beds and whatnot at the hospital, and we need resources on site, including the personnel resources, so that the humans need to be able to access work and have services of their own so that they are functioning themselves. So to do this, to enable this, we develop a human infrastructure as an additional lifeline, adding a mathematical representation of this lifeline with updated interdependencies and shared states in the model. The paper that I'm describing today includes additional discussion of the need for an all hazards and probabilistic approach to the hazards, measures of performance and adaptive capacity and baselines, and more of these kinds of things can be revisited from these new perspectives. So by taking a new perspective, we get new insights. And so I'm not going to go over all of this. There's quite a lot written about this in the paper, but I thought I'd mention a few pieces of this that I thought was valuable for this discussion. So here I talk about in this slide about the different hazards and some of the elements that we might consider in the hazards themselves. But I think what I want to spend a little more time on is this idea of taking a SIBS perspective or a service-based perspective, as we do in the constructs 4 and 5, and noting by incorporating that soft infrastructure, we can gain new insights into resilience, and even into the hazards themselves. And this table is about primary, secondary, and tertiary impacts of hazards that become noticeable by taking this new way of looking at it, using a new lens that comes from reframing the problems. So just as an example, if we take, I know, flooding, a primary event might be that the courthouses are flooded. Secondary is that the access routes to the courthouses are flooded, so you can't get to the courthouses. And then third is that the roadway repair and cleanup crews on flooded access roads block the pathways from the neighborhoods, preventing critical personnel from reaching the courthouse. So we wouldn't have actually thought of this as a hazard or hazardous in a way that would affect the resilience of the system we were looking at unless we started thinking about that service approach or a SIBS-based approach. And so there's a lot more on this in the paper. The idea of measuring resilience in terms of continuity of service, which is really underlying a lot of what I'm talking about here, suggests that the resilience of a technical system can be judged based on key performance metrics relevant to that system and the services it provides, which was embedded in the examples I gave. So we can think about the hospital had one of the notions for resilience of the hospital system was waiting times, fatalities, those kinds of things. For the transport of cargo through a port, we would focus more on throughput. So we use different metrics, even if those metrics are only to support an agnostic resilience metric. So they're embedded underneath it. And this is true even when we talk about time to recovery, time to getting back to a certain level. We're still talking about a level of performance that is a function of functionality, and we have to decide what that functionality means. So are we taking the human's perspective, the user's perspective, or are we taking the engineered systems perspective? The performance measurement used in resilience assessment depends on the application, as I just mentioned, and I think it also affects the mathematical form we use. And this table, which goes on for 2 slides, is showing examples of performance measures in different application areas that I found in the literature and the corresponding mathematical form that was taken in those studies. You'll see this table in the paper as well. The choice of a baseline can greatly affect the values of many resilience metrics. So I mentioned just a moment ago the idea of time until returning to a certain level of performance. But you can also use it in other ways. It might be, your resilience metric may be a function of your performance post-event compared to your performance pre-event or something like this. But the right baseline depends on the construct or perspective that is taken. And we saw this in particular with the users of the transit system, and that there are different baselines for different populations. Populations that are a mobility challenge will have different baselines, for example. And this is something that isn't really talked about very much in the literature, and yet is critical and sort of like a hidden piece of the resilience metrics, particularly when we use agnostic metrics. And the last key thing I want to share my thoughts on today has to do with inequity. So there are unintended inequities that may be hidden in the actions we take, and particularly when we use only a technical perspective on thinking about what actions to take. So actions can be taken to protect large portions of the community. And when we do that, we may do that at the expense of a few. So we may disproportionately affect some people from a certain location or demographic. One example that I've come across in some unrelated work had to do with construction of sea walls to combat the effects of climate change and sea level rise. And what we notice is that the construction may protect high value property while negatively impacting poorer communities or the communities that have to live around the actual infrastructure. Resilience metrics may be weighted by population. So we have an underlying bias that shifts protections away from less populous areas and puts it onto larger populations. So you think about using an expected number of people who gain something from the system. And when you do that, you're going to serve the masses and you're going to forget about the few. In this particular case, I think of the Arctic, where we have an unrelated project, but I think about the people in the Arctic who are bearing the burden of climate change as their permafrost that their infrastructure is built on is thawing, and they have new events of flooding and high temperatures that are affecting their ice, which affects their ability to get their food. And all of that they're bearing because we are focused on the masses and not the few who live in these sort of remote locations, but who may be taking on the burden of the world's changes that may be coming from even the highly populated populations who are, making the most or causing the most greenhouse gases and so on. So there's this underlying bias in the metric that we choose to use that could shift the protection away from the less populous areas, and these populations may not be arbitrary. They might be poorer communities or communities from certain ethnicities and so on. And likewise, we may lean toward larger businesses and away from smaller minority-owned businesses. And this happened during the initial stages of COVID lockdowns, where the larger businesses thrived in meal delivery and things like this, and the smaller minority-owned businesses really suffered. A service-based analysis then can help illuminate some of these hidden biases and eliminate some of these inequities that are hidden from when we take the engineered perspective. So to wrap this up, framing resilience affects the metrics, the perspectives, the baselines, and perspective and application help us frame our, and create a framing construct that we might not even realize we're doing. And these together affect the model, the solution methods, the data needs for quantifying resilience. And ultimately, my key aims were to illuminate the hidden role of framing, the effects of measured values, intentional action, which components and systems are included, performance evaluation and resilience conclusions, and to connect engineering to the people of these systems that the systems are actually designed to serve. The webinar and today, just now, in the IISE transaction perspective paper on which this webinar is based, was built on years of work in infrastructure resilience quantification, which involved many wonderful people, oops, one second, who I want to recognize here. And I never give a talk anymore these days without giving a shout out to the journal that we have launched from IISE. It's an Elsevier journal that seeks to tackle global challenges with analytics, mathematical modeling, and operations research. And so I hope you'll check that journal out and think about it for your own publications. Finally, please feel free to reach out to me. My email address is here. And I thank you to this audience here today for your interest and your time, for joining me to hear these thoughts. And I thank you for inviting me to share these thoughts, the paper and this webinar.